I want to spend some time today talking about backpropagation, and then eventually we're going to get here, which is a topology aware language model trainer, which is a backpropagation based trainer that I made specifically for transformer models. And I'll get into this in a second. But before we dive into this, I've been thinking along these tracks and about this subject for, I don't know, a few years now, honestly. And uh, I think there's a lot of researchers that have problems overall with backpropagation within LLM models, within neural networks, etc. Backpropagation was invented by Geoffrey Hinton in the 1980s. Before this, models didn't utilize it, and then backpropagation utilizes gradient descent to essentially pass the forward mechanisms and then the prediction between the forward prediction and the actual answer, and then it passes that back over the weights and then back propagates them back over the weights. In simplistic terms, like in like real world terms, the best analogy, like the philosophical analogy that I can come up with for what back propagation is and how it works is utilitarianism. That's what back propagation is, right? And my problem with utilitarianism is the same problem with backpropagation, right? Which is that it's not real world, meaning that in a real world environment, you don't know the answer. Like, you're not given the answer in advance, right? You're not said, okay, you did this, and then here's exactly what you did wrong. And then you go through, and then, okay, I can piece back exactly what I did wrong. Like 90% of the time, you don't know what you did wrong. And that's life. But that's not how these models operate. They operate in a world where you're given the correct answer after the fact, and then they self-correct based off of that. And it's just a different mechanism. It's a different world, right? If the world operated under these pretenses, then utilitarianism would be the best model in the world. Right? There would be unequivocally utilitarianism would be the best. So if we're putting a model into this environment, then why not maximize it? Is kind of the next step that I get towards, right? So the problem is pretty simple in terms of framing, that backpropagation isn't a natural concept. I understand that. A majority of researchers understand that, right? And then a lot of researchers, and I'll put myself in that camp included, have problems with backpropagation overall because of that. It's always thought that backpropagation is like a pit stop in the off ramp, right? We're going to get past it because biologically speaking, nothing uses backpropagation. So there's some sort of mechanism that we're missing. What that mechanism is, I don't know. But the other mechanism that we're missing is how exactly do we get these models to like interpret their environments and then make decisions based off of their environments. And we don't know how to do that either. Right? So there's two things that we don't know within this. But combining those things, if we take a step back from that philosophical approach, we take a step, okay, let's ignore the fact that backpropagation is, there's no biological equivalent for it. Is it philosophically justified? Because that's not a philosophical justification to exclude it entirely, right? Okay, it's not natural, it's not biological, okay? But that doesn't philosophically preclude it. So is it philosophically good? And then that's kind of like the next train of thought I come up with within that. And then within that, I start thinking, okay, in order to prove that, how I can prove that is if I can come up with a mechanism that utilizes and relies solely on backpropagation. If I couldn't utilize this mechanism without backpropagation, then that would be philosophically good instance of backpropagation, right? Backpropagation would be needed to exist in that instance. And then so I start playing around with this concept. And then as you're aware, you've been watching my videos, I've started diving deep into this concept of AI geometry, AI math, and the concept of like these neural nodes and these neural network groups. And then when I tie all of this together, what I realize is that the best way to actually get the model to learn and to update itself via these mechanisms is through backpropagation. I need backpropagation in order for AI geometry to work, in order for AI math to work. And so working backwards from there, come up with essentially the topology aware backwards propagation mechanism, which I'm still working out the full math and the paper on. I'll show that and I'll release that probably in about a week or so. But today, what I have for you is the topology aware language model trainer. And then this utilizes pre-trained models and it will pre-train a model on this topology aware mechanism. And then so going through the code, it's very straightforward, right? I define a topology aware trainer. And then so in this instance, it uses attention entropy, attention sparsity, and density. These are the metrics that I want, right? So it's entropy, sparsity, and density. And then utilizing these metrics, I can control the backpropagation of the mechanism, right? So entropy, meaning like how confused the model is. Sparsity, how much information it has on this concept. And then density, how much of that information is being stored like in the layers itself and in the connections. And then that's really what we're measuring within that, right? And then so within this, I initialize an initial state. And then this is the funny thing within all of this to me, right? So I initialize an initial state and it's just a random state. I pick random numbers for all of it. I'm like, here's your initial state for all these numbers. That looks good. And then train it essentially on this, right? And then I want to record and understand these mechanisms. So again, the entropy, the density, and the sparsity. So attention, density, and sparsity. And then going through and then measuring these specific components within this. And then I give it like two training mechanisms or two training sentences within this, which is quantum computing is on the horizon and data privacy is crucial. I use my favorite models to do this, the small LLM models, because I can load them into anything. And then when I run this, I did have T4 turned on. In this instance, I changed the runtime because I don't like Google. They charge you for T4 instances over like for more than a day, so I turned it off. But so you want T4 on, but when you run it, here's the magic, right? So we run and then we get our graph, and then we're measuring three things in this instance, right? And attention entropy, attention sparsity, and density of the nodes, the neural network density, right? And then so we want entropy to go down, sparsity to go down, and density to go up. So entropy clearly goes down, right? This is clearly trending down. We have our orange, which is sparsity, clearly trending down, not as much as entropy, but clearly trending down. And then our density clearly trending up. So in this instance, with this trainer, what we can clearly see from this graph, this is what has been updated, right? So that the topology of the networks, of the weights within the model has been updated. And then that's really what I want to get down to within all of this, right? Like more and more what is coming out is that geometry matters a lot within this, right? How the model stores the information, how exactly to me, it's essentially, it's taking data, words, language, etc., and it's reshaping them into different geometric shapes. And then in this instance, how it does that is entropy, sparsity, and density. Nodes, clusters, and edges. I've talked about this a lot, right? These are the building blocks of all of this. And then when you put all these concepts together, you can control the way and understand how much the model is learning, how much is not learning, how much information is needed, etc., via the shapes that it's producing and the weights of the shapes. And then so that's what we're analyzing within this. Really cool in this instance to me, because you can, by measuring these shapes, get a much clearer picture than a loss rate. Right? I can tell you entropy is going down, sparsity is going down, and density is going up. That's very clear, as opposed to loss rate went from 1.0 to 0.8. Like I'm just presenting a different way to go through this. I'll link to this collab notebook. And then again, this is a stepping stone, right? So I do have a next level progression to this, which is essentially just, it will be like a backpropagation 2.0. But this is utilizing that an offshoot of that research, building this out for transformer models. And here you go. So if you like this type of content, please like and subscribe. Thank you very much.